Okay, so we have been, it has been a while since we last time talking about the lecture content, but I do appreciate of your presentations. A lot of them, I think we are going to have a pretty decent final presentation at the end of this quarter. But you know, like before before the end of the final week, we still have quite a few things that we can discuss about regarding this content of the class. So where we end before the presentations is this. We were talking about we have a lot of new memory technologies. You know, like every time like I'm learning new things. So like recently we are putting a proposal together with the CHIPS Act, and then my collaborators, they tell me that they have new like memory technologies, and all of them sounds very promising on the paper. But you know, sometimes you really need to see if you can put things in practice, if you can find the manufacturers who are willing to produce it. So those are the so those are the big question marks that we have on this bulk of the memories. So a lot of people are talking about, yeah, we have resistance memory, they have pretty short latency, but do you really see them in your computer systems, right? So that's actually the like manufacturing put into real production is probably the largest issues with new memory technologies. And we talk about why memory is so important, because a lot of applications, they are memory bounded. And for memory bounded applications, we need, well, and sometimes faster memory technologies, as I mentioned, they are probably not ready yet. And even though they are ready yet, we still cannot find anything that could actually surpass the latency that like DRAM provided or the SRAM provided. So it turns out you have to figure out if we can increase the bandwidth or lower the data volume. So the last time we talked about, well, if you want to increase the bandwidth, the controller speed matters. And where's the controller is actually on your processor. So that's why CPU still matters. So recently I'm thinking about upgrading one of the oldest machine in my lab. And I started to look at some of the specs that we have. And turns out that, well, even for the same generation of the processor, like these two processors, they are at the same generation. But sometimes you will figure out even for the same generation, the memory speed that you can support is different. And the reason is just because the frequency of the processor core, they are different. So sometimes a lot of people are thinking about, well, we are now in the era of GPU, so we don't care about the CPU performance. And the answer is probably not, because a lot of people, when they purchase the GPU servers, they have no knowledge about architecture. So they pick a processor that is relatively slow. So what does that mean is that you are also getting a pretty slow memory performance. So for example, like this machine, if you pick the right-hand side, then you can only support your memory at this frequency. However, if you pick the left-hand side one, then you can have a memory, you can have slightly higher memory frequency, right? So so it turns out that if you can ramp up your controller speed to DDR5 600, then this is the theoretical bandwidth that you can achieve. So the last time we ended our discussion at this pieces of a code, which I don't know if how many of you remember, right? So this is a code that I meant we have a pretty deep discussion regarding what's the intention of the code. And turns out the intention of the code is that we try to measure the read bandwidth. And the way why we want to initialize this array as a fixed number instead of like random number is because a lot of you probably are not aware that random number generation is a very, very time consuming and very compute intensive operation. So although it sounds like, okay, just pick a random number. So sometimes that's a very interesting thing, right? Like, well, even for you, right? If I want you to think out a random number, it would take you quite a lot of time, right? So random number is actually a pretty interesting problem to work with. And I'm a little bit surprised that I don't hear anyone talking about random number in your presentation this time. But maybe in the future, if you are searching for a research problem, I do think random number has its own value. But here, right, let's set it aside. Random number generation is actually a pretty time-consuming, very very compute-intensive operation. And our code here, we are intended to measure the write performance. So that's why I want to just initialize it as once. So okay, another question some of you might be thinking about is that why don't I initialize it as zeros? Right. So the thing is, 0 is a very, very, very interesting number in computer science because we know people love to initialize things as zeros. So in our computer systems, we actually have done a lot of optimizations in initializing things to 0. So one of the examples is in the operating system level. If you have a page that contains all zeros, then turns out it's a no op. So that's why you cannot initialize things as 0. Because if you initialize things as 0, then some cases, the system optimization would actually make it no op. Like in some of the operating systems, they actually provide a page that contains all zeros. Right, so you probably remember, right, copy on write, right? So the easiest thing to do is that, okay, I always prepare a page that is always 0, right? So if you initialize it at 0, then I would just put everything, I would just link all the pages that are containing zeros or all the arrays that are containing zeros to that physical location in the very beginning, right? And only when you try to modify the content, I will start allocating it. But what does that mean is that if you are continuously writing zeros to that place, it won't even do anything, right? So you cannot initialize it as 0. So that's why I'm putting ones here instead of zeros here, right? So even though like this code looks very obvious, trivial, understanding the intention behind it would actually be very interesting to see, right? And the reason why, like I have 2 separate loops. One is like writing it for the ones, and the other is writing it for 10 times. As many of you know, is helping us to separate the phenomenon of page fault. So that's where we were the last time. And what we haven't done the last time is that look at the result, right? So again, after you write a program, it's really important to be able to analyze the result. A lot of students that I have interacted with, I think the biggest issue is that, okay, I ran the result, I have no way to interpret the result. So a lot of us, we would like to be an engineer. However, what's a valuable engineer and what distinguishes senior engineer and the junior engineer is that the senior engineer, they can look at the result and figure out what's going on, right? So look at the numbers. What did you learn? What did you learn? This is the right latency. The left-hand side is the latency. The right-hand side is the bandwidth. Look at both numbers. What did you learn? What?
Under a page is the same access latency for.
Okay, so here's the thing, right? The first thing that you will see, under a certain point, everyone has the same latency, right? And if you figure out what that number is, right, it's probably not too difficult for you to guess what's going on, because everything under one page, again, right, we talk about the memory organization. The row buffer is exactly the size of a page, right? So what does that mean is that no matter what you read, as long as it's smaller than the size of the row buffer, I will have to wait for the DRAM to fill the whole row buffer before I can do anything, right? So everything below 4K is probably going to enjoy the same latency, right? So what does that mean is that if you have request that is smaller than 4K, because they are only having the same latency, they are all having the same latency, right? So what does that mean is that the more you read within this latency, the higher bandwidth that you are going to get, right? So the best practice is that if your data initially comes from DRAM, you should try to read the same page as much as possible before you go to another page, because what's going on here is very obvious, right? It's pretty much like an exponential growth, the linear growth on this, because every boundary of 4K is going to trigger another page fault, as well as a row buffer access, right? So, and this effect is actually clear up when you have this like 10 times average, because when you do this for 10 times, it's very likely that a lot of stuff, they are already in a row buffer, so you don't have to suffer from this page fault overhead. So you can pretty much look at this, right? So this gap is pretty much telling you what's the overhead of the page fault, right? So those are the interesting things that you can learn. There are some, there are some other points. A lot of people, when you talk about the result, you will say, well, what about the L1 cache? What about the L2 cache? What about the L3 cache? But here the thing is that because the majority of the driving factor here is probably the row buffer and the page fault. So you don't see anything specifically that is related to L1 cache and L2 cache, because maybe they do have an effect, but the thing is that the majority is already taken by the overhead of page fault and row buffer. So you don't actually see the performance coming up from there. Okay, so another thing that you could look at is that look at the bandwidth, right? So here, okay, so this is sometimes difficult to see. So if we take a look of the priori Jupyter notebook, right? So here's the bandwidth that we are getting at this point. So with the first run, we only get like 5 gigabytes per second, right? And remember, we are running this system with a pretty advanced processor. So 5 gigabytes per second is probably too much, right? So too slow. So can you have a quick discussion and discuss what's the difference between the left-hand side and the right-hand side in terms of the memory write operations?
Just one integer or multiple integers? So the 31st bit one? For that specific one?
All right. So, can I hear what's your voice about what do you guys think about this pieces of code? What does that mean? What's the difference between left hand and right hand side? Okay, Hunter, what do you think?
We're looking this up. We think like this is using like a vector processing unit of the CPU. That's just using like linear, like looking up each individual like cell at a time. So for a performance implication, right? We would think that the left-hand side would better at performance, given the fact that you're doing a lot. You're doing 256 writes in parallel in comparison to the individual writes of the right memory.
So, okay. Any other thoughts?
So if the right-hand side code would already be sufficient to build the like memory controller, like there's no difference changing to the left side. Like if the bottleneck is the memory controller, I think the bottleneck is already here. So no matter how you want to write it, it's still gonna be a bottleneck.
Okay, so what do you think?
Well, I mean, we saw from the performance, we're only getting like 10 gigabytes per second. I think we didn't saturate the bandwidth yet.
Yeah, but why didn't we saturate the bandwidth?
Because we're not moving enough data.
Because we don't move enough data? Because of why? Why don't we move enough data?
Because a single instruction only moves 8 bytes.
And a single instruction only moves 8 bytes. And why doesn't that give us good enough bandwidth?
Because bandwidth is the amount of data you move over time. So this is.
But are they moving different amount of data?
But per unit time, one instruction will do more work than.
Okay, but why does that help? Why having? Okay, so first of all, here's the CPU memory bus, right? And if we have 64-bit processors, you have a 64-bit wide front-end bus between your DRAM and memory controller, right? So what Hunter said, you said you are moving 256-bit per every time. That's probably not true because your front-end bus is only 64-bit.
One instruction does more work compared to.
Yeah, one instruction does more work, but why one instruction does more work would help in this situation.
64-bit for one instruction.
64-bit for one instruction, yeah, but what does 64, like 256 in one instruction would help?
You're writing to 256 pieces of data.
Yeah, but I only have a 64-bit wide bus. That's for the data and the instruction. What does that mean?
256 bits, so you're overloading the CPU memory plus one.
In what way?
Well, you're using all 64 bits instead of just measuring.
Yeah, but if I do the original write, right, it's also 64-bit. I'm writing a double every time, right? Why the right-hand side would help? Why can't I pipeline the original case? If I move 8 bytes per instruction, why can't I pipeline it? Elvin, what do you think? I cannot pipeline it because it's for scalar.
So if you are using different robot or something, they can have a better pipeline strategy or something.
Okay, so very interesting. What does that mean by a bus? So, like in the very beginning, I tried to emphasize the difference between interconnect and bus. What does that mean by bus? Okay, first of all, for bus, at any cycle, you can only have one-way transaction, right? So what does that mean? And also, bus means that everyone has to be synchronized in timing. So first of all, to trigger a write operation, you need a few cycles in the very beginning. And you have to send some signals, saying some signaling, right? You need to have some kind of signaling saying that, for example, if you see this, this is a write, right? So this is like a very initial signal. And then you can start sending your data. And after you send your data, again, your signaling would have some kind of like postfix to tell that the transaction is done, right? And because this is only one way, so at this moment, only one direction can do this, right? Now, if you do it every 8 byte, what does that mean is that for every 64-bit, you need to pay the overhead of this prefix and postfix. However, if you can do it in vector instructions, right? Although you still have to pay the same overhead in prefix and postfix. However, this part, you can actually have it like 256 bits, and then you have the postfix. So this is why you have better bandwidth utilization. Question?
I have a question on the cache. So basically, I think we first write the cache, and maybe for after some time, the cache then move to DRAM.
Right.
But for now, we're not like writing through the cache. So why is it different? So like, for example, if I write like 64 by 64 bit, I'm writing to the cache, and maybe the cache received enough, and then I write to the memory. So they are basically the same if you have the cache. Is it to understanding right?
So if you have the cache, okay, that would have another different thing. That would have different story. So for the cache, if you use, okay, so here, if you are reading data, okay, it only makes difference if you are reading. So if you are reading data from the cache, if you use vector instructions, your data will be fit into the vector registers instead of the regular register. So that will have a different story. Make sense?
So I mean, different story. I'm thinking like DRAM to cache.
So you are saying about DRAM to cache. So you are saying about reading it.
Yeah, I mean, like for writing it, from other understandings, like you don't directly write to DRAM, instead you write to cache, and then after some time, the cache synchronizes with the DRAM.
Right. So you need some kind of so here's the thing, right? So for this particular program, right, we will make it in a DRAM, right? If you call like a synchronization at the end, right?
So I mean, in that code given, I think we are writing to the cache instead of directly writing to the DRAM. So I would think for example, if I write a 64 by 64 bit, we are writing to the cache, but where the changes will not directly reflect in the DRAM.
No. So here's the thing, right? So that's the trick why you need to do it several times, and why do you need to? So if you check the program, right, it actually do it several times, right? So it actually would create the effect of flushing the cache content to the DRAM. So so here's the thing, the program itself does force the data to go into the DRAM.
Okay.
Right.
But normally it's not for every write will.
Right. But in this particular case, this is what we do. Okay? But does that explain why you really need to have one instruction does as many, like move as many data as possible? Right? So if today I want to move data from DRAM, cache to DRAM, for example, right? If you could use vector instructions, you should, right? So in this way, you are actually getting better bandwidth, right? So we can have a demo on this, right? So right now, let's do this. So let me run this SIMD version. And as you can see, the bandwidth I'm getting, right, is now, like even for the first run, right? Originally, the first one, I can only get like 5 gigabytes per second. But right now, I'm getting as high as 36, right? And this is like a DDR5 system. So it makes sense for us to get this kind of bandwidth. So this is pretty much like you are fully utilizing your bandwidth. And let's do the performance comparison, right? So right now we add two other figures, and then you can see, right? Even for the first run, right, the latency is a lot shorter. The latency is a lot shorter, right? Because we are using the SIMD instruction, right? So that tells you we pretty much minimize the per read latency in this way, right? But it also means that, right, because we are moving more data at the same time, so you can see like when initially, right, the latency doesn't increase because the main overhead is coming from the page fault and row buffering, right? But right now, because we have the SIMD instruction to help, so moving data is actually not that much. So you can see the actual page fault handling is actually not as scary as you can see from the result, right? And so you can conclude that our initial guess saying that everything is about like the row page fault or row buffering is probably not right, right? It's probably not right because if you can fix this, you can fix this part with SIMD instruction. It means that another thing is actually going to kill our performance more than the row buffering and page fault. That's probably your handling of your memory instructions, right? So this is what we probably would learn, right? So actually, sometimes you think about, okay, I just write the code in the same way as I did, but the thing is that if you move data one by one, it's a very, very, very bad practice in memory access latency, right? And in terms of bandwidth, you also see a very significant jump when you apply this SIMD instruction. So actually go from like 1 orders of magnitude, right? So if you want to write, the most efficient way is that you probably have to think about how can you fully utilize the SIMD nature. Question?
Why is the 10x average for write and write with SMD pretty much the same along with the bandwidth?
Well, because at that moment, right, a lot of, as I said, a lot of page is already created, and some of the stuff, they are well buffered. So that's the time you are going to see the effect of buffering and caching effect coming up.
So would the compiler like optimize to SIMD instruction?
So the answer is yes or no. If your code is pretty regular, it's possible for the compiler to generate that. But another thing is that only if the compiler intended to generate the code that is incompatible with some of the processors, then it will be able to do that. So sometimes you probably do need to add instructions like -m AVX to enable those. And also, when we say like enable AVX, it will do the most conservative version of the AVX. However, some of the processor, like the Xeon processor, they support AVX 512. And if you are compiling the code with just regular AVX, it's probably only going to support like 256. So you're still underperforming. Okay, question?
I just want to make sure I'm understanding. Right? So you're saying at a certain time we're still moving the same amount of data because it's 64-bit. It's just we're not paying the pre-charge time.
Right. Okay. Yeah. Okay, so that's why we want. And sometimes I want to know if I am maximizing my bandwidth, right? Or how do I know the bandwidth of my system, right? Then there's a good command code, DMID code, and you can put -t memory, and it will tell you what's the capacity of the total capacity of your system and what each memory module is running. So for example, here I have a memory module which is DDR5, support up to 4.8 gigahertz. However, if you see the configured memory speed, it's 3.6. And here's the reason for that, because each processor, they have their maximum capacity. And for this particular processor, because I installed 4 modules, so it turns out each module is only running at this speed. But what does that mean is because you have dual channels, so each channel is going to be delivering, each channel is going to be able to deliver 28.8 gigabyte per second. So if you have dual channels, you are still going to get like 57 in this case. So although each module is at this speed, but if you have dual module, dual channel, then this twice amount of speed is what you are going to get. All right. So now a lot of you heard about GDDR, right? The graphics version of the GDDR, right? So how does like GPU increase the bandwidth, right? So the GDDR standard, they actually have a lot higher bandwidth than we see here, right? So here we are saying like each module, they can only deliver like 20 to 28 gigabyte per second. So the idea of GDDR, they actually combine a lot of different things. So if you check about the math that we have been doing with, right? So here, how do we calculate the bandwidth? There are 2 factors. One is the controller speed. However, as you can imagine, the controller speed is something difficult to bump up, right? Because if you really want to support like hundreds of gigabytes, right, you need a controller that's probably running at 10 gigahertz. That's too crazy, right? So another factor that you can potentially increase is this, right? Here, we are having 8 chips in parallel, so we can read 8 bits of data at the same time, right? So what GDDR does are the following. First of all, instead of reading 8 bits of data at the same time, each column axis is right now reading 32 to 64 bit at the same time. So what does that mean is that, okay, saying that even though my DRAM is as slow as 500 megahertz, with 32-bit reading at the same time, I can already achieve 64 gigabyte per second bandwidth, right? So previously on CPU, you have a pretty high frequency memory controller and you cannot even achieve this bandwidth. But with GPU, as long as I have more parallel bits that are reading together, I'm able to achieve this high bandwidth with just one single module, right? But again, where's the cost? Why am I putting the controller to be only 500 megahertz at this point? It's because if you want to control more parallel bits, right, you can imagine because of the wiring, so your frequency cannot be too high. So there's a trade-off here. However, even with this trade-off, you are going to see higher bandwidth. But what's the cost of running your, some of you might be wondering, right? Why don't I just let my CPU memory controller or memory module organize it in this way, right? What's the cost of running this controller at a slower speed? What's the cost? Latency, right? Because what does that mean is that, well, you remember that signaling that we are talking about, right? So each of this is actually a cycle, right? So on the CPU, each of the cycle is only like 0.2 nanosecond. But if you are running it at 5 gigahertz, each of this cycle is actually 2 nanoseconds. So the latency could be 10 times lower if you want to support this high bandwidth, right? So this is one thing that GDDR does. However, that's not the only thing that GDDR does. So in addition, GDDR introduced another concept called channels. So instead of just having one module, one channel, one unit to receive memory command at the same time, GDDR actually has a lot more channels that can be command controlled in parallel. So, and each channel is a single unit that can receive memory request at the same cycle. So previously, we have been talking about banks and channels, and I was questioning some of you, do you know what's the difference between a channel and a bank? So to be honest, there's only one slight difference. So first of all, both banks and channels, they would allow operations to perform in parallel. However, what really makes a difference between channel and a bank is that each channel, they have their own unit to receive a command. So within the same cycle, you can issue multiple commands to multiple channels. However, if it's in the same channel, but just different bank, you can only issue one command to this channel. And you can only control another bank within the channel in a different cycle. So that's the difference. That's the difference, right? So GDDR here, they maximize the bandwidth, use the concept of channels. So what does that mean is that, okay, I can actually have multiple channels being controlled at the same time. But what does that mean is that I really need a super wide bus to send out data at the same time, right? So like some of the high-end GPU, so like for the low-end NVIDIA GPUs, they probably use like 192-bit bus. And some of the high-end ones, they have 384, right? So what does that mean is that at any cycle, I can send this 384 bits in parallel to all the channels that I have. However, as you see here, right, each channel I can only receive 32 to 64 at the same time, right? So it must be divided into multiple channels at the same time, right? So how do you know how many channels do you have, right? The thing is that you can probably see, oh, what's the in your GPU spec, what's the bus width, right? And then divide it by the parallel bits per channel, and then you know how many channels do I have, right? So saying that, right? If I have if I have 12 modules, right, which would pretty much be what's the okay? So if I have 384, right? So that would, and if each of them is like 32, right? That will give me like 384, right? So saying that I have a total of 12 channels on my GPU, then turns out that I can support this 768 gigabyte per second bandwidth in total, right? So this is going to be aligned with the total memory bandwidth that you see on your GPU, right? So what does that mean is that, right, if you pay attention to this, 64 times 12 equal to 768. And this controller is only running at 500 megahertz. So your GPU actually have a very, very slow memory controller. But the only reason why it has wider bandwidth is just because you have more channels, more parallel bits at the same time. So you trade latency with parallelism, right? So reading data from the device memory of your GPU to your SM is actually a very, very slow process, right? So that's why if you really want to optimize your GPU code, you have to figure out how to fully leverage your L2 cache, L1 cache, or even shared memory, right? So here are some of the bandwidths of the process of the GPUs, like for like a 4070, right? You will see like the only reason why they can sell the 4070 Ti a lot more expensive than others is because it equipped it with like 256 bit width for the memory standard, right? Okay, so let me see, what's this demo about? Okay, so for this particular machine that I use for demo, well, or sometimes if you really want to know what kind of GPUs that I have, right, a good command to use is probably NVIDIA SMI. So, and if you do like NVIDIA SMI-A, that will tell you everything. So for this particular computer, I'm running it, okay, so I think this is out. Is this? Yeah, I think this is right. Okay, so for this particular computer, I am actually having a GPU with 4070 Ti Super. And as you can see, for this particular one, let's see, what kind of information am I getting? It will tell you like how much memory being used, how much the total memory capacity, and what else? Power reading. Okay, clock cycles, right? And here you can see your memory controller is only running at 400 megahertz, right? So the GPU doesn't have really fast memory controllers. No, just because it's typically that slow. As I said, right, if you want to support that high bandwidth, your controller doesn't have to be that fast, right? Okay. So this is the right. So with like 4070, right, you can do a simple math and you can figure out that, well, your bandwidth is probably something like this, right? And the thing is that, right, you can actually subdividing your signal in some sense, right? So if you could try to divide your signal in different levels, like instead of just 0 and 1s, and if you can do a better quantization, or say like better sensing or of your signal, then you can actually, for one cycle, you can actually read 2 bits of data, right? So instead of having my signal always going up to 0 and 1, another thing that DDR. Okay, so let me go this, right? So for 4070, they advertise it as 504. But if you do the math calculation, you will figure out I'm only getting 252, right? So why the bandwidth is actually double? And the reason is that for the DDR6 technology, they took another tweak on their signaling. Is that traditionally, when we think about the interpretation of your wave, we only have 0 and 1. But for DDR6X signaling, they actually are able to subdivide the wave threshold voltage, set multiple threshold voltage to be like either 10, 11, 01, and 00. Right? So in this way, it's pretty much like multi-bits per cycle. Right? So that's how they double up the bandwidth. Right? So right now you have seen there are so many ways, but here's the cost again. If you want to sense this kind of signal, right? First of all, your sense amplifiers has to be specifically designed. And also, if you want to better sense multiple threshold voltage, it will force your memory controller to operate at an even lower speed, right? Otherwise, you won't be able to sense this because your circuit is going to be more complicated, right? So there's always a cost of making things more complicated. But what does that mean is that right now, if you can see what NVIDIA does to optimize the memory bandwidth. First of all, more parallel bits at the same time. Second, more channels at the same time. Now, more bits at the same cycle, right? So that's how they make it happen. So another company, AMD in the past, they advertised the idea of high bandwidth memory. So high bandwidth memory is a pretty straightforward idea in my perspective. So first of all, what they do is that, okay, so instead of, so for the multi-channel idea, right, I have multiple channels go to different memory modules, and my controller is running at a slower speed. But the high bandwidth memory idea is actually, okay, instead, and the reason why I can only have this limited amount of bits is because they are connecting the chip and the memory through copper wires that's on your expansion card. And the idea of HBM is that, okay, instead of adding memory modules that are separated from my chip, since we have more advanced packaging technologies, what if we stack them together as a single chip? So you might be wondering, what's the benefit of stacking them as a single chip? So this figure tells you why. So the thing is that if you are using a silicon interposer to connect your GPU die and the DRAM die as a single chip, because it's a silicon wire, silicon substrate on a chip, so the wires can be made smaller. So within the same area, you are able to put more wires in. So what does that mean is I can actually create an even wider bus than the copper wires to transfer data at the same time. So I would say high bandwidth memory is a very brute force technology in a way that we don't actually invent. There's no innovation here, to be honest. It's the innovation is from the hardware side, from the manufacturing, the packaging side, that we make the wires smaller. And then we just brute forcefully give you wider bandwidth, wider bit width in a bus, and then it happens. Right? So technology-wise, I would say it's less innovative in terms of computer architecture. It's more of an advance of material science and the EE technology in a way that right now, since you have more parallel, you have more bits that you can move on the bus, you naturally get higher bandwidth. Right? So that's the idea of HBM. But here's the thing. Well, if you want to make this happen, you need to build this silicon interposer, which is very expensive. Right? Okay, so now, well, we can have a quick wrap up. So you see processors using GDDR and HBM, right? What's the pros and cons of each, and under what situation you will pick one over another?
Material science problem, right? So you stack them on top of each other, but you just have very short wires, have very high bandwidth right on top of each other, right? And GDDR was spreading out and using parallelism to leverage more bandwidth, right? So when would we use parallelism? When would we use very fast bandwidth?
GDR now like the 36. When you have HBM, is there a chance you're reading the top DRAM instead of like one closer to the bus? Is that a latency effect?
Well, I mean, if it's DRAM, you should make it uniform. Otherwise, you are building a non-UMA like NUMA system.
GDDR, like the high-end cluster for site computing.
With a higher cost.
All right, what do you guys think? GDDR versus HBM. Which side are you going to use? Under what situation? Any idea? Okay, why? Because HBM is expensive. Okay, what others?
There's a thermal issue with the die stacking.
All right, so here's the thing. A lot of people might think, okay, why don't I just like, okay, even though I have a lot of money, right? Why don't I just like stack as, like make it wider or stack as many layers as possible? The answer is that you can't, because there's going to be a thermal issue, right? If you have more stacks, if you put everything within a small tiny area, that actually make the heat dissipation a lot more difficult, right? So a lot of people might think about, okay, 3D die stacking is going to help us get rid of the discontinuation of DNOT scaling, right? The DNOT scaling is saying that the more advanced the technology, the per transistor power consumption is not going down. And the per transistor power consumption is in relation to the temperature, the heat that's generated per transistor, right? So some people, like, I don't want to say who, but I do heard like some professor, they say, well, it would help, the like 3D die stacking would help alleviate the not scaling. And I counter argue that, and I got this confirmation from Intel as well, is that actually it will make it worse, right? Because in the past, it's just one layer. So if you dissipate it, no matter which layer you are, it directly goes out. But right now, it will affect another layer. So what does that mean? Is that the lower layer, because the heat goes up, right? It will heat up another layer, right? So it actually add up the heat, right? So 3D die stacking is actually challenging the heat dissipation very, very significantly, right? So that's why even with 3D die stacking, right, you will see like those HBM equipped GPUs, they cannot have a lot more memory than you can ever imagine because it can't. Otherwise, it will be a super hot chip, right? There's a conference called Hot Chip. That's probably where it comes from, right? And also the other thing, right? So that's why even though it has wider bandwidth, we don't use HBM everywhere. The cost, right? And another thing to think about is that it actually limits the freedom regarding how much memory you can put on the design, right? So for example, if I really want to produce a super fancy GPU card, right, I can actually put twice the amount of memory easily if it's on GDDR6, right? But with HBM, because the chip is already manufactured in this way, you cannot add more memory to it, right? So in terms of manufacturing flexibility, it would give people more flexibility in making the expansion card they'd like to be. So that's why more consumer cards. So whenever you see a third-party vendor publish a card, that's typically a non-HBM version of the NVIDIA chip because they want that flexibility, right? But for the HBM one, they are pretty only limited to data center segments because those are only possible by NVIDIA themselves. Okay, so let's take a quick look of this piece of code and tell me the intention of this code and what do you think the performance could change when size varies. Hunter, do you have a question? HBM.
Is 3D die stacking able to reduce like the area of it since you're kind of like instead of going out wider, you go in taller?
Well, if you go taller, right? Again, that's a heat dissipation problem.
So like my question is like kind of like saying it's like given like where you have like systems where space is kind of like a luxury, like kind of like space travel, something like that. Would that like
so you can build like a yeah, I mean you can build an empire tower, right? 3D stacking, but the thing is that two problems. You're still limited by the heat, and the other thing is that the only substrate that can send data is the last, right? So you are still limited by the outgoing bandwidth of the whole memory tower, right? So there's not really significant benefits of that, right? All right.
Oh,
All right, what do you guys think? What's the code? This is pretty trivial, right? What's the program? What's the program? What's the program about? Am I measuring the right latency?
We're doing a mem set before mem copy.
We are doing the main set and then
Mem copy.
main copy. And which latency am I measuring?
Mem copy.
Main copy. Okay. So what's the bandwidth or the latency going to be different from the previous one?
Now the caches are involved. If the the question asked about the promise size, right? When the promise size changes.
Right.
So when it's smaller, it should stay in cache.
What's mem copy?
Moving to
Okay, what kind of operations are within a move? Read and write. So previously you only have writes, but now this time the read is over in the play, right? And how does the size will make a difference? Yeah, but how about the bandwidth? Okay, so previously we measure a bandwidth pretty much like 50 gigabyte per second in the previous writes, right? For this one, how much are you expecting? Why?
Like you're counting the total time I'm reading and writing.
Mm-hmm.
So the total time should be double, and so you have like half the bandwidth.
Okay. Is this a very important type of code? Yes? In what sense?
You're always moving data around.
You are always moving data around, but do you always copy data around? Okay, so the answer is yes. 5% of cycles in Google's data centers. In one of the papers that published before. But can you think about a reason why in data centers we have so many memory copies?
I forgot the general word for it.
You don't want once if your node goes down, not everything can just explode, right? So you need backflow.
But I'm saying
It's like every time you spawn
I don't say like you think that user is like let's say
so every time you want to
right? So it makes sense that let's say you're manipulating the lines, right? You don't want to lose your visual right? Maybe doing some data manipulation, right? And that data is formed.
copy it, and then
You don't want your picture of a dog or something like that.
until then.
But you still want to use that picture of dog to kind of like generate some image.
I was thinking more of like database use. Like for example, the internet. I don't want this search page to just disappear forever with all that stuff.
oh,
If you're ever like risking data to modify it,
node explodes, right? Just something goes wrong. The wire gets disconnected. You surge somewhere, and then just like the machine dies. So it's like you might have like the data, and then you do a mem copy and write to a CPU layer.
I don't know.
Yeah, it's embedded systems. And then we also learned about like how was it each time you spawn the process.
All right, what do you guys think about why we have so many main copies in data centers? 5% of the time, some of you might think, okay, who cares about that 5% of the time? But for the company, every penny matters, right? So if you can eliminate that 5% of the time, right, it will help the company a lot, right? So 5% of the cycles. Why we have to spend that 5% of the cycles in Google's data centers?
One thing I thought about was resiliency, because Google obviously the data center there's a bunch of data. One of the nodes goes down, like a machine dies or something. Definitely want something to replace it.
Okay, replica. But can we kick that out? No, okay. So that's not something we can kick out, right? What else?
Another thing may be like have performance computing, they distribute their data for different nodes. So
Okay.
collect them, then you can
Okay, data distribution. What else?
In a data center, they might be receiving a lot of like requests.
Requests.
And then with like the wireless profile stack, you need to do a mem copy for each of like the.
Okay, it's only wireless. Do we do wireless in data centers?
Oh no.
But okay, how many of you took computer networking class before? Okay, so here's the networking protocol, right? So although we say we have 7 layers, but we only have 5 layers in practice. And for the 5 layers, right, the application layers, for example, HTTPS, FTP, SSH, RTSP, right? They are all so-called applications. How do applications interpret data, right? So what typically during a network transaction, no matter it's wireless or wired, all the stuff you just mentioned, like I want to do replica, I want to distribute my data, they all go through this 5-layer protocols, right? So the very first thing to do is that my application layer, I would have data created. And then I put a header inside this bulk of data saying that what's my intention of sending you this data, right? It could be write to another machine. It could be upload. It could be download, right? So that's the header, right? So each application level packet, they would have a header plus the data. Now, it's not done yet because for the application, we only know there is an application, they want to do this, but we don't know how to send it out. So there's another layer called transport layer. So you must heard TCP, UDP a lot. They tell you, so it's pretty much like, okay, how many of you still know envelopes and mails? Okay, physical mails. Okay, that's good. Because sometimes I'm really like hesitate to talk about this like grandfather old things, right? Like I don't even check my physical mailbox that often. Like last time I finally went to the mail room in my ECE department, and then I figured out, oh, there was a student sending me a Christmas card like 4 months ago, and I didn't check it out, right? So if you want to send me a card, don't send us through. Just do an email. That's probably faster. And the thing is that okay, right? Once you, so what do you want? What do you want for a mail envelope, right? So the card is probably the content, right? And on the envelope, right, you write who you are, where's the source, where's the destination, right? So how do this, and the other thing is that how are you going to send it out, right? A stamp, you need a stamp, right? You need a postage, right? So transport layer is pretty much like tell you, Do you want to do it by ground? Do you want to do it by mail? Do you want to do it like signature required? Do you want to do it like a priority? Right? So this is pretty much like what a TCP UDP would do. So TCP means that it's pretty much like a signature required with tracking information, right? Like TCP means that when you deliver the packet, let me know you delivered it. Give me an acknowledgement. And UDP is more like, like what you would do if you want to send like junk mails. UDP is what you need, right? Because UDP means that just send it out. Doesn't matter if the other party receive it or not, right? So that's UDP. And RTP is more like a protocol for like people doing YouTube, right? So it's controlling, deliver this before this amount of time. If it's not reaching there yet, just discard it, right? Because you don't want to see a frame back to the past, right? So that's another protocol. So with that, what does that mean is that for the transport layer, I would add another header. It's pretty much like on your envelope, I would add stamps in addition to the source and the destination, right? And then there's another protocol called network layer. So I would say network layer is pretty much like, there are some like, it's pretty much like, okay, so now so on the network layer is pretty much how determine the route to deliver this mail or this package, right? So that's why you need an IP address, right? With that address, so it's pretty much like, okay, why we have this postal code and the state on your physical mail address, right? So the same thing, like for IP address, it has different segment, and based on the segment, I would decide how to route this packet, right? So so there are a few protocols there, like the IP protocol define the standard how we should formulate our network address. The ARP address resolution protocol tell us how to figure out where is each IP address, right? And ICMP knowing if this machine is up or down, right? So those are the networking protocol. And again, you would add another header, and this header is pretty much tell you which IP address should you deliver this to, right? So the IP address, the network layer, it defines the global routing of how to deliver this packet. And then per link, between each link of the global routing, how to deliver it, if it's successful or not, that's by this link layer protocol. So the only difference between wireless and wired network is actually just at this link layer protocol. So like wireless protocol like IEEE 802.11, that means that you are going to use the link layer protocol of wireless network, Wi-Fi network, to deliver your packet. And if you are using Ethernet, it's 802.3. And then finally, again, you still need to add a header there. And finally, you will use the physical layer. How do I modulate the data? And on the other hand, right, so that's why we have so many memory copies, right? First of all, each of the packet, they will go through different buffers. And each of the buffer, you need to have a copy of the previous content plus previous header. And they are in different layers, right? In different layers, they have different buffers, and they are in different sizes. So sometimes you need to segment it, right? So that's why you have so many memory copies, right? Every time you need to do memory copy, do checksum, memory copy, and checksum, right? So in data centers, there are many uses of mem copy, like creating network packets, right? So that's why CPU matters. Because right now, the network interface card doesn't do a lot for you. It's the CPU generating the up 3 layers of packets for you, right? And that's why, so some people will wonder, okay, why NVIDIA purchased Mellanox, a high-speed network interface card company. And the reason is because right now, for all the data centers, why Intel still matters because they control the speed of sending out packets, right? With Mellanox, it's possible for high performance data centers to just directly use all NVIDIA solution to interconnect, right? So that's the use case of main copy. So so it's probably not too difficult to imagine the main copy. But the thing is that if you look at the main copy bandwidth that we measured, even with the SIMD enabled, we are only getting like 25 at the very top, right? So it's definitely underperforming, underutilized the bandwidth in many, many cases, right? Especially, okay, if you want to get really high performance, you want from larger sizes. But if you check the size of your internet packets, most of the time, they are not this big, right? So which means that in a lot of cases, when you create packets, your performance is probably something like that, right? So that's actually a pretty big problem to talk about, right? So since we are running out of time, I will leave it to the next lecture. But other than that, enjoy the rest of your day. I will see you on Thursday.
Is it important to take networking if you want to go in that?